All right, welcome back everybody. We are now ready to start the video on nebular condensation theory. This is going to be video 3 in our lecture module 1. Still adapting to this new system. Hopefully by the end of this, I'll be pretty proficient at this. But let's go ahead and get moving. So, going to bring back up our slides so we can start nebular condensation theory. All right, so here we are on nebular theory. Again, got to make this full screen. All right, so here we are. So, nebular theory. This is going to be what explains the structure of the solar system. What is our starting point? How does our solar system actually begin? And how do planetary systems in general begin? So if you look out in outer space, you'll notice that there are lots of collections of gas and dust. These are regions that are denser than most. We've already looked at a few of these in class. So whenever we looked at the picture of the pillars of creation, which I encourage you to go ahead and Google and look at those, that would be a type of nebula, which is just a collection of gas and dust in outer space, where you can form new stars and new planetary systems. So out in space, we have this large cloud of gas and dust. It's just hanging out and doing what it does, just happy as it is. It's going to have some sort of set net rotation because everything in the universe has some net rotation. And it's just going to be happy as it is until something happens. There'll be some event that's going to trigger the nebula to start to collapse. It's going to get compressed. It's going to be pressed from all sides, which is going to make it so now gravity is a little bit stronger than the thermal pressure that was keeping it a nice, steady, stable cloud. And gravity is now going to start to dominate, and it's going to cause the cloud to start to collapse. It's going to make the cloud shrink. It's going to be getting smaller and smaller and smaller. So what type of event can kick off this gravitational collapse of a nebula? So there are a variety of them, but I just want to share a few of them with you. So we could have a supernova explosion. So a nearby high mass star, don't even have to be that nearby actually, explodes. Sends out this enormous shock wave that goes rippling throughout space. It would hit this dense cloud, wrap around the cloud, and push it inward from all sides. Kind of a cool little historical fact. We didn't really have a good handle on this as a mechanism until we looked at nuclear bomb tests, which we saw whenever they set up little villages to see the effects of nuclear bombs. Actually tragic, hard to watch videos, but you see the explosion, and they saw in the video that the shock wave would surround a house and cause it to implode before it get blown away. So that is one thing that can trigger a gravitational collapse of a nebula, so it can form a planetary system, and very likely the mechanism that formed our solar system. You can just have a nearby hot star that is born. It's going to, again, being hot and massive, send out a shock wave that can compress a cloud and cause it to collapse. It could be that one of the arms in the Milky Way sweeps past, and that can also compress the clouds and start the gravitational collapse. So lots of mechanisms can get these nebulae out in outer space, these collections of gas and dust, to start to collapse. What is going to happen as they collapse? And now we just have to go with some physics. So it's going to have some net rotation, and as it collapses, as it becomes smaller and smaller and smaller, it's going to shrink and shrink and get smaller and smaller and smaller. And just like a figure skater, as they go into a spin, if they pull their arms in, pulling the mass towards their center, so just like as this cloud shrinks, that figure skater will start to spin around faster and faster and faster and faster. So as this cloud collapses, it'll have faster and faster and faster rotation. And just to cue you in the graphics I have over here, the white arrows are demonstrating the force of gravity. The red arrow is showing the rotation. So why does it actually spin faster and faster and faster as this cloud collapses? What is the physical mechanism at play here, and what are the consequences? So It spins faster, just like the figure skater. As they pull their arms in, they spin faster and faster and faster and faster. Why does that happen? Through what is called conservation of angular momentum. I know, it's a lot of words. It sounds like a big concept, but let's go ahead and break it down. We talked about Newton's first law of motion, that things in motion want to keep their exact same motion unless something tells them to do differently. That is really a statement of momentum. A heavy object is harder to stop. Once it gets moving, it's harder to change its motion. So angular momentum is going to be just the momentum of something that's in rotation. So something that's spinning around. It wants to keep spinning the exact same way. Conservation means that before and after is going to be the same amount of angular momentum. You cannot create more angular momentum or lose angular momentum. So the net angular momentum stays the same. So whenever a change happens, we have to figure out how the angular momentum is going to balance itself out so that the sum total is the same. And the way I like to think about this, if I were to get up, and sorry I can't really get up right now, and spin around with my arm out, and I was to say to hit a punching bag that has a pressure sensor, if I'm spinning with my arm all the way out, I don't have to spin very fast, and I could hit the bag and it would measure a reasonable force. Now if I pull my arm all the way in and I spin around again, if I wanted to hit that bag with the same amount of force, I'd have to spin faster. So really what we're seeing there is the idea of the conservation of angular momentum. As you pull the mass towards the center to have the same amount of momentum, angular momentum, you have to spin faster. So smaller overall radius means larger rotation. That would be an inversely proportional relationship. So as this cloud shrinks, it spins faster and faster and faster and faster. And now we have to consider how things are going to change. This ball of gas and dust is going to change as it rotates faster and faster and faster. So now forget the figure skaters. And now let's imagine a pizza parlor. Wish we could all go, but imagine there are still people out there making pizza. So we have a ball of pizza dough. And if I were to take this pizza dough and spin it and throw it up into the air, rotate it really, really quickly, what happens? Well, it flattens out into a disc shaped, a pizza shape. So as this cloud of gas collapses and spins faster and faster and faster, it's also naturally going to flatten itself into a disc. This is going to be the densest in the center and the central regions, and that's going to be what we call that dense mass at the center that's getting the majority of all the mass of the entire system, is going to be what is going to become our sun, our so-called protosun. It is on the pathway to become a star. But then we have this disk of gas and dust, and I have two representations of that shown here, that are rotating around this central mass, this central protosun. What do we call this entire collection of the protosun and this now disk of gas and dust? Well, it's still a collection of gas and dust in outer space, but now it is flattened into a disk and is rapidly rotating. So we call this rapidly rotating disk-shaped collection of gas and dust the solar nebula. It is the nebula that is going to become our solar system. So very appropriately named. Now, if we're talking about other planetary systems, it's the same process, but we can't call those the solar nebula because they're not forming the solar system. They're forming a different planetary system. So we call, in general, the idea of a solar nebula would be called a protoplanetary disk. So the solar nebula is an example of a protoplanetary disk. If you're forming these collections of rapidly rotating disk-shaped gas and dust around other stars, we call them protoplanetary disks. So now we have set the stage for forming our solar system that's going to be disk-shaped. And it was remarkably simple. All we had to do is start a collapse of a cloud of gas and dust in outer space, which we see everywhere. And naturally, As it collapses, it's going to rotate faster and faster and faster, which rotational physics will force that into forming a disk shape with everything rotating the same direction and most of the mass at the center, where we'll have this nice disk of gas and dust out of which we can form the planets. So it's in this collection of gas and dust around the protosun that is containing all the material that we can form the planets out of. This is where we're going to be forming our solid grains. What we're going to have to do is invoke condensation theory that's going to tell us what materials are where. So what kind of materials do we have in the inner region? Probably rock and metal, so we can form terrestrial planets. And then as we move further out, we'll add things like water ice and more cold temperature ices as we move further and further away from the protosun. Kind of makes logical sense, right? Farther away is going to be cooler. So nebular theory has given us our disk shape. It's giving us the building blocks to form the planets, and it has everything rotating in the same direction, which is the same direction that the sun rotates in. So far, this is doing a bang-up job of explaining all the evidence that we were talking about. Eventually, we have to go from initial tiny little building blocks, little grains of dust, to actually forming large planets and planet-sized objects. So we're going to have to gather all the dust together in a process called accretion. This will be our story of planet building. That is for a different video, so I'll hold off going into any more detail here. So let's see what we've accomplished, just as another reiteration. So nebular theory, as the cloud collapses, it rotates faster and faster and faster, which causes it to flatten out into a disk shape. We call this the net result, the rapidly rotating collection of gas and dust that is now shaped like a disk, the solar nebula that's going to form our solar system. The disk of gas and dust contains all the material to form the planets, and the planets are going to be forming out of the same kind of material that the sun is forming out of, and they're all going to be forming at the same time, giving us a common age for the solar system. We have the dust that can become the rocky stuff, the terrestrial stuff, but that's going to be a little bit more of an interesting story. Whenever we get to condensation theory, we're going to lose a lot of the dust because things are going to get hot and it'll vaporize. We have formed a flat system, so we have our disk shape. It's all rotating in the same direction. So we have explained the organized spin sense, and if you think about it a little bit, then it would make sense that if you formed a solid round body out of that, everything would be rotating in the same direction as well. We're going to have to gather up all the material that's there, all this very, very low dense space-like gas and dust material. The densities are slightly better than vacuums we have here on Earth. We're going to have to concentrate that all down into planets, forcing all of that material into a very, very small volume relatively. So we're going to end up with isolated planets. I apologize for all the construction sounds. If you're hearing those, they're doing significant work on my building at the moment, and there's nothing I can really do about those. Here we are in isolation. But here we have nebular theory. It has explained the structure of our solar system remarkably well. But does this really happen? So I want to give you some observational examples of this. So here are a bunch of protoplanetary disks that we see out there in different stages of formation, different times, different snapshots of their formation processes. So down here on the bottom left, these are protoplanetary disks that are seen edge on. So again, you're looking down the edge of the system. So we're seeing the edge of the disks. And here you can see the two protoplanetary disks that are in the Orion Nebula, which we just see lots of nebulae in the Orion Nebula. And all of these are forming planetary systems. Up here in Beta Pictoris, we can see the disk of material. The black central region is blocked out, is blocking out the starlight, so we can see the disk of material around it. And over here we have a later in the formation stage. This is the Fomalhaut system, and this ring of material, which we've now identified to be water ice, is where a planet is forming. So yes, we see those. We also have this wonderful high resolution in the radio and the microwave facility, this ALMA radio microwave interferometer, which has allowed us to view these disks directly. So here's a collection of 20 of them. Various stages of formation, but you can see they're all flat and disc-shaped, just as nebular theory predicts. And when you see these nice ringed structures, where there is a gap where you don't see anything, that is where a planet is forming. All the materials coming together to form a planet. So here's a collection of 20 protoplanetary disks. So yes, we now routinely observe these in nature. So we have the structure of the solar system, but we still have a very, very big question. How are we going to get the solid materials, the building blocks, such that we get the terrestrial planets and the inner parts, and then we add more and more icy material the farther we go out? And we have a problem with this. You can imagine as we compress everything, as this entire cloud collapses into the solar nebula, it's going to get very hot, meaning that most of the dust that was inherited from the nebula is going to get vaporized. It'll get so hot, it'll turn into a gas. Just like if you boil water, you get water hot enough, it turns into water vapor. You could cook a rock, it eventually melt into lava, and you keep cooking it, it would turn into silica oxide gas, silica dioxide gas, and a few other gases that could then recondense and form rocks if you cooled it back down. So we are going to lose most of our solids. How much we lose is an unanswered question in planetary science right now. And it's actually one of the questions I work on pretty significantly with my research, is understanding how much solid material is inherited from the nebula versus how much is vaporized and reformed. But the net thing is, we do know that the temperatures are going to make it so a significant amount of the original dust is vaporized and we get to reform it. And it's how we're going to reform it, dictated by condensation theory, that explains our compositional gradient that we observe in our solar system. So just a reminder, what is the compositional gradient? How is condensation theory going to explain it? So the compositional gradient, the inner solar system, we have the terrestrial planets that are made out of rock and metal. So we better create building blocks, solid bits, solid dust grains, solid particles that are only metal and rock. Then as we move further out, we go into the asteroid belt. As we move to the outer regions of where the asteroid belt was forming, we better be able to add in some organics to explain the C-type asteroids. As we move out past that to the giant planet region where we have the gas giant planets, we better be able to make things that are large enough to hold on to hydrogen and helium gas, making gas giant planets. And if we look at the moons of those systems, we better have water ice as a building block. Because if you look at Enceladus, or pretty much any of the moons of Jupiter and Saturn, they're about 50% metal and rock, 50% water ice. There's a smattering of other things, organics, and other ices as well. Then as we move into the ice giants, we're going to be adding even colder temperature ices, methane ice, ammonia ice, nitrogen ice. And as we move into the Kuiper belt, we no longer have the ability, something's going to fundamentally change. There's just not going to be a high enough density of material to form large objects anymore. So we're only going to form very small rocky, icy objects, our Kuiper belt objects, in a belt of a collection of up to billions of rocky, icy bodies, Kuiper belt objects. And these are going to have a whole slew of interesting ices that we don't normally see on Earth. Super cold temperature ices, our carbon monoxide ices, our ammonia ices, methane ices, nitrogen ices, things like that. So notice that as we move further and further out, we get colder and colder temperature materials. This is explained by condensation theory. This slide right here is just to review so we can clearly see what materials we need to build via condensation theory to form the planets as we observe them in the solar system. So I've made this so that we're looking edge on in the system. The sun is shown in the center. It should be a protosun rather than a picture of the sun, but we don't have a picture of the protosun. So I just used a picture of the sun. Then nearby the sun, we can only form terrestrial planet, so we're only going to have metal and rock as building blocks. As we move further and further away from the sun, temperatures are going to get colder. Eventually, they'll be cold enough where we can form water ice. And once we can form water ice, that distance away, we call that the ice line, we get a new ingredient, water ice. And for every 1 bit of metal and rock will form, we can form 2 bits of ice. So we get a new ingredient, we get a lot of it. And then as we move further and further out, by observing things like the Kuiper Belt objects, we know that we need to add these cold temperature, what I'm going to call exotic ices. So how do we explain that? How is condensation theory going to explain this gradient of building blocks? This is going to give us a compositional gradient that we observe in our solar system. And the key to this is that the solar nebula is not all the same temperature. It has a temperature gradient such that the inner regions, the places closest to the protosun, are the hottest. And then as you move further and further and further away from the protosun, it's going to get cooler and cooler and cooler. So temperatures are going to drop from about 1500 to 2000 Kelvin down to moderate temperatures, about 300 to 500 Kelvin, to less than 300 Kelvin, cold enough to form water ice, and then cooler and cooler and cooler the farther you go away. And if you think about it, it's not that surprising that we have this temperature gradient. Where is it going to be hottest? Of course it's going to be hottest near where the sun is forming, the central regions, and then it's going to get cooler and cooler and cooler the further you move out away from the protosun. And this temperature gradient is going to dictate what solid building blocks we can form. This is the heart of condensation theory. We have a temperature gradient, and we know what temperature is required for certain materials to go from the gaseous form to their solid form. This is a type of condensation. And I'm using the term condensation in a very familiar term that you're probably all aware of. Let's imagine that we've made it to summer, we're allowed to be back out into the world again, and we are enjoying some time on the beach. We get a nice, tall, cold glass of ice cold water. We set it down on the table, and what's going to happen to the outside of that glass? Well, you'll see that water collects on the outside of the glass. Nobody's really surprised by this. That water got there via condensation. Again, a term you've probably heard, and I'm using it in the familiar sense. So how did that water actually get on the outside of the glass? What is happening with that condensation? Well, the air has a certain amount of water vapor, gaseous water in it. The surface of that glass with that ice water in it is very, very, very cold. So that surface is cold enough to take that water vapor and turn it into liquid water that's collecting on the outside of the glass, condensation. So that is an example where we've gone from a gas to a liquid. What we're doing is going from a gas directly to a solid. So a better way to think about this is, hopefully we won't have any more of these this year, but you go to bed at night and overnight the temperatures plummet to freezing. And then you wake up the next morning and you look outside and you notice that there is a fine coating of ice crystals on the grass, on your windshield, causing you to have to scrape it, covering the trees. We have had a night of frost. How did that frost get there? Where did that water ice come from? Well, there is water vapor in the air, and as the temperatures drop below the freezing point of water, that water vapor condensed directly into water ice on all the surfaces. This is the type of condensation that we are going to be talking about in the solar nebula, going from a gas directly to the solid. That example of forming water ice frost is just one example. We could find the location in the solar nebula where the temperature is low enough to condense water vapor into water ice. We would call that the ice line, sometimes called the frost line. What about other materials? If you get things really, really hot, you could eventually turn rock into vapor. So there are all the building blocks. There are gases like silicate oxide gas, silicate dioxide gas that can condense to form Rock frost, little bits of rock. What temperatures do they happen at? What are their condensation temperatures? And if we order this list from highest temperature to lowest temperature of all the possible materials that we could condense out, we have a huge temperature range, so we'll get all of them. We have what we call a condensation sequence. By no means do you have to memorize these temperatures. If I want you to use the temperatures, I'm going to give you the temperatures on exam 2 and on the final exam. But let's walk through here and see what kind of solid frosts, solid building blocks we can get given the temperature. So we can form metal and oxides, little metal grains. And if you looked at my meteorite that I brought to class, you would notice there are little flecks of nearly pure iron in there. To form pure grains of iron, temperatures have to be 1700 Kelvin or lower. And you can take a gas and form metal grains. To form silicates, rocks, 1200 Kelvin or lower. Hydrated silicates, so you add a little bit of water or hydration to them, 700 Kelvin or lower. Organics, carbonaceous materials, 500 Kelvin or lower to drive organic chemistry. Water ice, 273 Kelvin, the freezing point of water. Given the pressures of the solar nebula, that's not the exact number, but it's easy for us to remember, so I'm going to go with the familiar numbers for water ice. Carbon dioxide, you can form carbon dioxide, it'll freeze out into a carbon dioxide frost, forming solid grains of carbon dioxide, also called dry ice, at 195 Kelvin, ammonia at 100 Kelvin, methane at 45 Kelvin, and nowhere in our solar nebula is it going to get cold enough where we can condense out hydrogen and helium, so that will remain a gas. Something to point out is that they were going to have this very important line that we call the ice line, that exterior to which, moving farther away from the sun, it'll be cold enough where we can add water ice as an ingredient. This is a really important thing to remember, because once we get past what we call this ice line, we not only have metal and rock with it primarily to form things out of, but we also have water ice, and we'll form a lot of water ice. For every 1 grain of rock metal that we form, we can form 2 grains of water ice. So let's now play this out in our solar nebula to see what building blocks we get where. So I've created here an image of looking at the edge of the solar nebula. So we're looking at this thing edge on, and it's as if I just chopped it in half. So here at the center, we have the protosun, and then we have the hotter regions of the solar nebula, and then it gets cooler and cooler and cooler the further we go out. At the bottom, I have a temperature bar of the temperatures of the solar nebula. So if the temperature is below the condensation temperature, we should be able to form, condense out, frost, little solid bits, our building blocks, to build the planets out of that material. So this is a question of what solid grains can form given the temperature of the solar nebula. So pretty much the entire solar nebula, other than the very, very most inner regions, which are closer in than where Mercury is going to be forming. But by the time you get to Mercury, the solar nebula would be 1200 Kelvin or less, meaning that you can condense out metal and rock everywhere. So throughout the solar nebula, we're going to get metal and rock grains as building blocks. And now is a great time to introduce, when I keep saying grains, dust particles, things like that, what are we really talking about? When these things condense out, they form very, very small, solid bits of material. How small? So the average particle that's forming is about 1/10 of a micron, 1/10 of a millionth of a meter. To give you some perspective, if you've been having any campfires or you've built a fire, whenever you see smoke, smoke is made out of particles. Smoke particles are about 1/10 of a micron in size. So these things are about the size of particles of smoke. But we're getting these tiny particles throughout the entire solar nebula. We have metal and rock as a building block. We move further out, and we will hit that ice line. There'll now be a point in the solar nebula where exterior to that, the temperature is below 273 Kelvin. It is cold enough to form water ice grains. So out past the ice line, we have a new ingredient. We have our metal and rock from before, but we now have water ice as well. Keep moving further and further out, you'll pass the carbon dioxide frost line, you'll pass the methane frost line, the ammonia frost line. So as you move further and further out, you'll start adding in what I'm calling these exotic ices. So any cold temperature ices. So in the outermost regions, you're going to get cold temperature ices. And the further out you go, the more types of ice you're going to get. So now you can see we have this gradient of material. We have metal and rock everywhere. Then we add in water ice, and then we keep adding in more and more cold temperature ices. And one other important thing, where are we getting organic chemistry happening? Anywhere where it's 500 Kelvin and below, so a little bit interior to the ice line and a little bit exterior to the ice line, we are getting organics. So right in this region, a little bit interior to the ice line, you'll be forming things like the C-type asteroids. What happens as we go further and further out? Well, the density of the solar nebula gets less and less and less. Just like the higher and higher you go up in the atmosphere, the farther away from our gravitational source we get, the thinner the atmosphere gets. The farther away you get from the protosun, the thinner the solar nebula gets. So in the outermost regions, the density starts dropping really, really quickly. And without a whole lot of material there packed together, you can't really form large objects anymore. So we'd expect that just past the ice line, where you have the most ingredients and a big volume of space, you can form very large things. And then as you move further and further away, we expect things to get smaller and smaller and smaller. Oops. So that ends our video on the solar nebula and nebular condensation theory. Where have we been left off? So I know I switched around to the slides a little bit. Let's go back to this ending slide. This is our starting point for our story of planet building. We have now explained the disk-like structure of the solar system, then the fact that everything's rotating and revolving the same way using nebular theory. We have also used condensation theory, just looked at the solar nebula will naturally have a temperature gradient, hotter in the inner regions, colder in the outer regions. And all we have to do is look at what the temperature is to see what solid materials we could form based on their condensation temperatures to get a compositional gradient of building blocks to build the planets out of. What remains is we have to put these small little smoke-sized particles together and form planet-sized objects. That is going to be the subject for our next video and lecture module 1. Thanks for tuning in, and I'll see you in the next video.